The spiky halo of light around the blotted out solar disk is the plasma from the sun's outer atmosphere or corona. Credit muratartShutterstock. Vyachesla Lukin is the program director for plasma physics and accelerator science at the U.S. National Science Foundation and an active researcher in the high-performance computational modeling of magnetized plasmas. His recent work has focused on the modeling of solar plasmas. Lukin contributed this article to Live Science's Expert Voices Opt Insights. On Monday, August 21, people in the United States will have the opportunity to turn their gaze skyward to see the moon eclipse the sun. Those in the path of totality will glimpse a complete eclipsing of the sun. Millions of Americans will don their special glasses and cross their fingers for perfect viewing conditions, but few may realize that the wisps of light they see emanating around the blotted-out solar disk are plumes of hot, charged gas called plasma from the sun's corona, or outer atmosphere, an extremely rare sight. That plasma fuels the solar flares and space weather that affect power grids and communications systems on Earth, and it continues to reveal mysteries that have yet to be solved. Plasma makes up 99.99% of the visible matter in the universe, the stars and the galaxies, and it also exists in many forms on our planet. It holds the promise to potentially change how we think about and harness energy, how we explore the solar system, and even how we might treat cancer and other diseases. Plasma physicists, including me, who study the sun will be exploring the eclipse view, and will undoubtedly learn more about the fundamental nature of this strange substance, which, unlike ordinary gases, is ionized or charged and hence considered a fourth state of matter. 10 solar eclipses that changed science. The field of plasma physics is relatively young, as this state wasn't identified until 1879, when it was referred to as radiant matter by English scientist Sir William Crookes. It was renamed plasma in 1928. We now know that plasma is present in objects that span a spectrum of scales, from finely engineered nanoscale radiation sources, to familiar halogen lamps and fluorescent light bulbs, to supernovae and galaxy clusters. Processes involving plasma also span tremendous scales of time, from attosecond, own a quintillionth of a second. X-ray laser particle interactions, 10 to the power of 18, can occur in a single second, to the regeneration and evolution of solar magnetic fields on a 22-year cycle, to the formation of galaxies over hundreds of millions of years. Researchers have been leveraging the common elements underlying that vast range of processes to gain new insights and harness plasma's power. Such studies have become the basis of many technological applications, such as microchip design, medical imaging, cancer treatments, space propulsion and better space weather prediction. Plasma research has also inspired designs for controlled fusion energy technology, an environmentally clean and virtually unlimited source of power. For those of us in its path of totality, the solar eclipse will reveal the complexity and beauty of the solar corona. Magnetic fields in the sun spawn the loops and spikes of plasma that are launched from the corona, something that astronomers using high-tech ground and space-based telescopes observe daily. The eclipse will provide an opportunity to see all of that activity with the brightness of the solar disk removed. Usually, the bright solar disk overpowers the glow from the sun's outer atmosphere. However, researchers also recreate and study those very same physical processes in miniature in laboratories across the United States and around the world. A 2-decade, ongoing partnership between the National Science Foundation and the U.S. Department of Energy is driving exploration of plasma in all its forms, and it is helping us understand plasma like never before. Total Solar Eclipse 2017. When, where and how to see it safely. Several of those studies are helping to solve a long-standing solar mystery. Why is the sun's corona more than 100 times hotter than its surface? The solution to the sun's temperature mystery likely begins with its magnetic dynamo. Turbulent plasma flows in the sun's dense interior, the miasma of incandescent plasma. If they might be giants' fame, generate tangled-up magnetic fields that emerge, expand, and untangle themselves in the corona. As they do so, the energy from the magnetic fields gets converted into heat, which gets released in dramatic fashion in the corona's tenuous plasma via myriad waves, shocks and flares that we can readily observe with modern telescopes. Yet answers to many questions of just how the plasma and the magnetic fields interact to heat the corona and to produce the flares remain unknown. A combination of ever better observations, highly sophisticated computer models, my field of research, and critical theoretical advances continue to improve our ability to explain why the sun, and ultimately the Earth's space environment, are the way they are. The process of magnetized plasma turbulence is not unique to the sun. It plays an equally important role in the formation of galaxies, the solar and stellar winds, and what may become one of the biggest societal applications of plasma physics-controlled fusion energy. Ever since the United States first tested the hydrogen bomb, a staged fusion device, 65 years ago on an island in the Pacific Ocean, scientists have dreamed of harnessing that same fusion energy, which also powers the core of the sun, in a controlled way for peaceful purposes. Today, several fusion reactor concepts are being pursued in the US and around the world as a safer alternative to nuclear power plants. Most of those concepts rely on the ability to confine a fusion plasma within magnetic fields. One of the keys to success will be to learn how to take advantage of nature's lessons to both heat and control the plasma, much in the same way that, on a much larger scale, the plasma is both heated and organized into well-defined structures in the sun's corona. Exploring nature from a plasma physics perspective allows us to revisit the very foundation of the way the universe works and what we think we understand, thereby advancing technology development. On August 21st, the total solar eclipse will pass by, spending up to 2 minutes and 40 seconds over each viewing area, and crossing the country in about 90 minutes. Afterward, many viewers will remove their eclipse glasses, post photos to social media and move on. NASA's total solar eclipse maps photos. However, for many plasma physicists like myself and my colleagues, it will be a special day. Scientists will have collected a new set of robust data about the corona, and we will all have taken another step in developing a more complete understanding of this fundamental state of matter and its place in the universe. Follow all of the expert voices, issues and debates, and become part of the discussion, on Facebook, Twitter and Google. The views expressed are those of the author and do not necessarily reflect the views of the publisher.